You know, if you work in a physical office building, the basic rules of security are actually entirely intuitive. You aren't going to like write down your personal banking password on a sticky note. Or, the keypad code to the server room on a neon yellow sticky note and just leave it slapped on your monitor for the cleaning crew to see.
Oh, absolutely not. I mean, that would trigger an immediate conversation with HR and the security team. It's just a universal, fundamental baseline of operational security.
Right. But the moment we step away from our physical desks and into the world of infrastructure as code, specifically using tools like HashiCorp Terraform, that physical intuition just seems to completely vanish for a lot of teams.
Yeah, it really has.
Engineers are effectively leaving digital sticky notes with the keys to their entire digital kingdom just scattered across their file systems, their version control history, and their CI/CD pipelines. So today, we're doing a deep dive into infrastructure as code security.
It's such a critical topic.
It really is.
Yeah.
Our sources today include documentation for HashiCorp Vault, AWS Secrets Manager, and study material for the Terraform Associate 003 exam. Our goal here is to help you, the listener, build a mental model of the clean desk policy for your infrastructure. We want to ensure sensitive data is never accidentally exposed while you're managing Terraform deployments.
Which is huge because managing sensitive state and secrets is easily one of the most heavily scrutinized areas of focus for infrastructure engineers right now.
Yeah, I'd imagine the stakes are getting higher.
Oh, massively. As companies scale their cloud footprints, the blast radius of a single compromised credential scales exponentially. You are no longer just exposing a single database. You might be exposing their root authentication token that allows an attacker to just drop your entire AWS organization.
Wow, just drop the whole thing.
Exactly. And this is a massive, unignorable component of the Terraform Associate 003 certification. You simply cannot pass that exam or, frankly, operate safely in a modern engineering environment without understanding the mechanics of how Terraform handles and mishandles secrets.
Okay, let's start by mapping out the vulnerability surface. Before we can talk about advanced secret management, we kind of need to know where these digital sticky notes are actually being left.
Yeah.
So in a standard Terraform workflow, where are the primary locations that secrets tend to leak?
Well, we can categorize the leaks into three primary vectors. The first is the most blatant, which is secrets hard-coded directly into your primary.tf configuration files, like your main.tf.
Right, and those get committed straight to Git.
Exactly, committed right to a version control system. The second vector involves placing secrets in variable definition of files. So specifically, your terraform.tfvars or the star.auto.tfvars files.
Okay, the tfvars files.
Yeah, HashiCorp designed these files to automatically load variable values during a run, right? And engineers just frequently commit them to version control out of pure convenience.
Just to make it easier to run the code locally.
Exactly. And then the third vector, and arguably the most insidious one because it happens entirely behind the scenes, is when secrets are stored as plaintext values inside the terraform.tfstate files.
Right. Okay, so configuration files, variable files, and state files. Let's look at the variable files first. There is this chilling real-world scenario from our sources today that I think illustrates the operational reality of this.
Oh, the database password one.
Yes, exactly. So an engineer is troubleshooting a database connection issue locally. And to test the connection, they just drop the production database master password into their local terraform.tfvars file.
Which happens all the time in the real world.
Right, so they get the infrastructure working, they run git add dot, they commit their code, and they push it up to the remote repository. And then 6 months go by.
That's the terrifying part.
6 whole months. Suddenly, during a routine security audit, that engineer realizes their .vars file containing that plaintext master password has just been sitting in a public GitHub repository the entire time.
Yeah.
Every bot, every scraper, every bad actor scanning GitHub has had access to it for half a year.
And, the time frame in that scenario is really what makes it so destructive. Automated scrapers can find a leaked credential in a public repository in literally a matter of seconds.
Seconds. Wow.
Oh, yeah. By the time the engineer realizes the mistake 6 months later, that credential has likely been traded, sold, or is being actively exploited by multiple parties.
Okay, let's unpack this.
Yeah.
Because I understand that committing a production password to a public repository is obviously a catastrophic mistake. But let me play devil's advocate here for a second.
Sure.
HashiCorp literally designed .vars files to hold our variables. It feels a bit, counterintuitive to say we shouldn't put our secret variables in the file specifically designed for variables.
Right.
And furthermore, Most enterprise teams aren't using public GitHub repositories, right? They are using private enterprise-managed repositories. So doesn't utilizing a private Git repository kind of solve this problem without needing to just abandon tfvars files entirely?
I hear that argument a lot, but relying on the privacy setting of your version control system is a classic failure of defense in depth.
How so?
Well, private repositories are compromised constantly, access tokens leak, employee laptops are stolen, disgruntled employees walk out the door with cloned repositories on a thumb drive.
Right, human error is always a factor.
Exactly, and occasionally a private repository gets accidentally flipped to public during a system migration. It happens. If your database passwords, your API keys, and TLS certificates are sitting in plaintext inside a private repository, you're relying entirely on the perimeter defense of Git.
So if one thing fails, the whole castle falls.
Yes. One compromised developer endpoint gives an attacker read access to literally every secret in your infrastructure. And this brings us back to that core concept of the clean desk policy. True security isn't about, hiding the sticky note under your keyboard or locking it in a drawer where someone could eventually find it. It is about fundamentally eliminating the presence of the secret from the file system.
The secret just simply shouldn't exist in your source code at all.
Exactly.
So you're making sure the password is never even written down inside the office in the first place.
Right.
So if we accept that 2 out of our 3 major leak vectors involve files being committed to Git, right, the .tf files and the .tvars files, then our absolute baseline defense has to be ensuring Git never sees these files, even locally.
That is precisely where a rigorously maintained .gitignore file becomes absolutely mandatory.
It's like a bouncer at an exclusive club.
That's a great way to put it.
The .gitignore file is the bouncer, and it's holding this VIP do not enter list. So who is on that list?
For any Terraform project, there are specific patterns that just must be ignored. You need to ignore the .terraform directory, which holds localized provider binaries and shouldn't be versioned anyway. But crucially for security, you must ignore terraform.tfstate, terraform.tfstate.backup, any file ending in star.tvars, and local override files like override.pf.
Because if we go back to that breach example earlier, if that star.tvars pattern had been on the bouncers list, that developer physically couldn't have accidentally pushed the password to GitHub.
Exactly. By enforcing that .gitignore policy, we cleanly sever the connection between the files a developer might use for localized testing and the shared version control system.
It acts as an automated safety net.
It does. But as we move down the list of leak vectors, keeping variables out of Git is really only step 1.
Right, because eventually Terraform actually has to run.
Yeah.
We've kept the variables out of version control, but Terraform still needs the actual database password to provision the database. Now, HashiCorp provides a specific feature for handling sensitive data within the configuration, which is the sensitive equals true flag. You can apply this argument to your variable declarations in your output blocks. And when you flag a variable as sensitive, Terraform suppresses the display of that value in the command line interface.
That's correct.
So if you run a Terraform plan or a Terraform apply, instead of printing out your actual database password in the terminal, it just prints out the word sensitive wrapped in brackets.
And it is an excellent feature for preventing screen surfing. If you are sharing your screen on a Zoom call or someone is walking behind your desk, your terminal output is nicely sanitized.
Right.
But what's fascinating here is that this specific feature is the focal point of a massive illusion of security. And it is a critical trap that frequently catches candidates taking the Terraform Associate 003 exam.
Oh, really? Let's explore that trap. Because on the surface, sensitive equals true sounds like HashiCorp has just provided a built-in security solution. Problem solved, right?
Right. And the exam tests your understanding of the boundaries of Terraform's features. The trap is believing that adding sensitive equals true instructs Terraform to encrypt that value when it writes it to your disk.
And it doesn't.
It absolutely does not. The sensitive flag is purely a cosmetic mask for the standard output stream in your terminal. That's it.
Wait, really?
Yeah. When Terraform completes its run, it generates the terraform.tfstate file, which is just a large JSON document mapping your configuration to the real-world resources. Inside that JSON file, sitting on your local hard drive, that quote-unquote sensitive variable is stored completely in plaintext.
You have got to be kidding me.
It is entirely readable by anyone or any process that can open the file.
Wait, so if it only hides the password on my computer screen but leaves it completely readable in the state file,
Yeah.
isn't that just a dangerous false sense of security? I want to push back on HashiCorp's design choice here.
Go for it.
From a user experience perspective, if I explicitly tell a security-focused tool that a piece of data is sensitive and it hides it on my screen but then writes it in plaintext to a file on my hard drive, that feels like a massive footgun. Why doesn't Terraform just hash or encrypt the password in the state file automatically?
I get that frustration, but it comes down to the fundamental architecture of how declarative infrastructure actually works.
Okay, explain that.
Terraform operates by calculating a delta, right? A difference between what you want your infrastructure to look like and what it actually looks like out in the real world. To calculate that delta, it has to know the current reality.
Oh, I see where this is going.
Yeah, if Terraform were to hash your database password in the state file, and then you change the password in your code, Terraform would have absolutely no way to compare the hashed version against the new plaintext version to see if a change actually needs to be made.
Because hashes are one way.
Exactly. It requires the raw data to compute the execution plan. It needs the real values, so it stores them.
Okay, that makes sense from an engineering standpoint, but man, it leaves us with a massive vulnerability.
Right.
If I run Terraform locally, I now just have a local file containing all my production secrets. If I'm working on a team and we share that state file, the problem just multiplies.
This is exactly why local state is almost never used in production environments. To secure the state file, you have to move it off your local machine entirely by configuring a remote backend.
Right.
You instruct Terraform to write the state file directly to a remote location like an AWS S3 bucket or HashiCorp's Terraform cloud.
But wait, moving the file to S3 doesn't magically encrypt the JSON data inside it, does it?
No, that JSON remains exactly the same. The security mechanism shifts to the storage layer itself.
Yep.
When you use an S3 backend, you enable server-side encryption, typically using AWS Key Management Service or KMS. So you are encrypting the bucket at rest. Furthermore, you use IAM policies to strictly lock down who can even read that bucket.
So you restrict access to only the specific CI/CD roles that actually execute the Terraform pipelines.
Precisely. A human engineer should almost never have read access to the production state bucket.
Okay, so we are building out our clean desk policy step by step here. We use .gitignore to prevent localized files from leaking into Git.
Yep.
We use remote backends with KMS encryption to ensure the state file isn't just sitting on a developer's unencrypted hard drive. But we still have a core problem. We stopped using .tfvars files entirely. So how do we actually pass the secrets into Terraform when it runs?
We have to transition away from static files entirely and move toward runtime injection.
Runtime injection.
Yes. The most universally supported method for this in Terraform is utilizing environment variables. Terraform is literally programmed to automatically look for environment variables in the system that start with the prefix tf_var_ followed by the variable name.
Oh, so if your configuration expects a variable called db_password.
You export an environment variable named tf_var_db_password directly into your shell session.
Okay, I see the progression here. Instead of saving the password to a permanent file on my disk, I'm just holding it in the temporary memory of my terminal session. When I close the terminal, the environment variable is destroyed.
Exactly. But honestly, humans shouldn't really be running production. Terraform applies from their local laptops anyway.
Fair point.
The true power of environment variables is unlocked when you integrate them into CI/CD systems, like GitHub Actions or GitLab CI. The pipeline runner spins up an ephemeral temporary container. The CI/CD system securely injects the secret into that container's memory as a tf_var environment variable. Terraform executes, provisions the infrastructure, and then the container is instantly destroyed, just wiping the memory totally clean.
That sounds incredibly clean, but let's look one layer deeper. To inject the secret as an environment variable, GitHub Actions still needs to know what the secret is in the first place.
True.
So haven't we just moved our digital sticky note from a .vars file into the settings page of our GitHub repository?
That's a great question.
And furthermore, for Terraform to provision resources in AWS, GitHub Actions needs AWS credentials. Are we storing long-lived AWS access keys inside GitHub? Because that just sounds like another static secret waiting to be compromised.
That is the exact critical thinking required at this level of infrastructure design. If you manually paste an AWS access key into GitHub secrets, yes, you have just created another static vulnerability.
Right.
This is where OpenID Connect, or OIDC, becomes absolutely essential. Instead of giving GitHub a password to access AWS, you establish a cryptographic trust relationship between your AWS account and your GitHub repository.
But how does that trust relationship work without a password?
AWS is configured to recognize the specific identity of your GitHub repository. So when the GitHub pipeline runs, it generates a short-lived, cryptographically signed token proving its identity.
Okay.
It hands that token to AWS. AWS validates the signature, confirms the repository is trusted, and issues temporary, highly scoped credentials that are only valid for the exact duration of the pipeline run. There are no static AWS keys stored anywhere.
Wow. That eliminates the AWS credential problem entirely. But what about the database password itself? If we want to move beyond just injecting it from the CI/CD platform, the sources detail using cloud-native secret managers, specifically utilizing the Terraform data block.
Yes.
How does AWS Secrets Manager fundamentally change the way Terraform interacts with sensitive data?
Using a data source represents a massive shift from quote-unquote pushing secrets into Terraform to having Terraform pull them dynamically. Instead of defining a variable and pushing the password into it, you configure the Terraform AWS provider to reach out to AWS Secrets Manager during the execution phase.
Oh, so it happens during the run itself.
Exactly. You write a configuration block that essentially says, do not expect a variable for the database password. Instead, query AWS Secrets Manager for the secret name production DB key and use whatever value it returns.
So if we go back to our mental model, Terraform is no longer being handed a piece of paper with the password written on it.
Right.
We are giving Terraform a map to a highly secure lockbox. We are saying, go to this specific lockbox in AWS, use your temporary OIDC credentials to open it, retrieve the contents, provision the database, and shut the box.
Yes, that is a perfect analogy.
The password never touches our source code, it never touches the GitHub secrets page, and it's fetched over an encrypted API call at the exact moment it is needed.
And operationally, this centralizes your security management, which is huge. If the security team decides the database password needs to be rotated, they don't have to touch your Terraform code. They don't have to update GitHub Actions.
They just change it in the lockbox.
They simply rotate the value inside AWS Secrets Manager. The next time Terraform runs, it dynamically fetches the new value.
That is a remarkably robust architecture. But I want to take this to the absolute logical conclusion.
Let's do it.
Even with AWS Secrets Manager, we are still relying on a static string of text, right? Someone or some process generated a password and stored it in a lockbox. If an attacker manages to compromise the IAM permissions and read that lockbox, or if a disgruntled employee viewed the password in the AWS console yesterday before their access was revoked, that static string is still valid today.
Unfortunately, yes.
So to reach the absolute pinnacle of the clean desk policy, we have to look at HashiCorp Vault and this concept of dynamic secrets.
And this is the paradigm shift. Every method we have discussed so far, environment variables, CI/CD injection, AWS Secrets Manager, they all involve securely transporting a static, pre-existing secret. HashiCorp Vault's dynamic secrets engine completely eliminates the existence of the static secret.
Break down the mechanics of how that physically works. When Terraform asks Vault for a database credential, what is Vault actually doing behind the scenes?
Well, Vault is configured with a highly privileged root-level connection to your target database. When the Terraform pipeline executes and requests a credential via the Vault provider, Vault does not reach into storage to retrieve a saved password.
Okay.
Instead, Vault physically connects to the database in real time, executes a create user command, generates a highly complex randomized password for that specific user, and hands that brand new credential back to Terraform.
So it literally creates the login credentials out of thin air, on demand, strictly for that single pipeline run.
Precisely out of thin air. But the generation is really only half the magic. Vault attaches a strict time to live, or TTL, to that credential.
Okay, what does that mean in practice?
Let's say the TTL is configured for 15 minutes. The moment Vault hands the credential to Terraform, a countdown begins. Terraform uses the credential to provision the necessary infrastructure. Once the 15 minutes expire, Vault automatically reaches back into the database and executes a drop use error command.
Oh, wow.
The credential is completely revoked and destroyed at the database level.
It operates exactly like a hotel key card.
Yes.
When you check into a hotel, the front desk doesn't hand you a master skeleton key, and they don't give you a key that works indefinitely. They give you a piece of plastic programmed to open your specific door for the exact duration of your stay.
Right.
The minute you check out, the system revokes the authorization. The card becomes useless plastic.
Yeah.
You could drop it in the parking lot, someone could pick it up, and wouldn't grant them access to anything.
That analogy perfectly captures the mechanism. Even if a highly sophisticated attacker manages to intercept the credential while Terraform is using it, or if they somehow extract the plaintext value from the encrypted remote state file later that afternoon, their efforts are entirely wasted.
Because the door is already locked.
By the time they attempt to authenticate with the database, the user account simply does not exist.
This fundamentally alters how engineering teams approach trust and access. You are no longer trying to build an impenetrable fortress around a static password. You are architecting a system where the data itself is ephemeral. The blast radius of a leaked credential shrinks from catastrophic organizational compromise to just a 15-minute window of limited access.
And when you synthesize all of these concepts, you achieve the true clean desk policy. There are no .tfvars files lingering on local hard drives. The version control history is completely sanitized through strict .gitignore enforcement. The tfstate files are locked away in remote KMS encrypted buckets.
Yep.
Long-lived cloud credentials are removed from CI/CD pipelines using OIDC trust relationships. And finally, the secrets themselves are generated and destroyed dynamically by HashiCorp Vault. There is nothing left for an attacker to steal because the sticky notes effectively self-destruct the moment you finish reading them.
It is a remarkable evolution from where we started, going from an engineer accidentally pushing a production password to GitHub to a fully automated pipeline generating cryptographic trust and ephemeral database access in mere milliseconds.
And to you, the listener, whether you are currently studying for the Terraform Associate 003 exam, or you are tasked with auditing your own company's deployment pipelines tomorrow morning, internalizing this progression is vital.
Absolutely vital.
The industry is moving away from perimeter defense and toward ephemeral, zero-trust architectures. Understanding how to navigate the limitations of the sensitive flag, how to properly secure your state, and how to implement runtime injection, that is what separates the novices from the professionals in modern infrastructure engineering.
It really challenges us to rethink the very nature of sensitive data. Which leaves us with a rather fascinating concept to ponder as we wrap up this deep dive. We spent decades building complex vaults, managers, and encryption layers to protect the passwords we create.
We have.
But if automated systems like HashiCorp Vault can dynamically generate, utilize, and completely revoke credentials across our entire infrastructure without human intervention, are we rapidly approaching a future where human engineers will never actually know or even have the ability to know a single production password ever again?
It's entirely possible.
Are we witnessing the complete extinction of the digital sticky note? Something for you to think about the next time your system prompts you to create new password. Thanks for joining us on this deep dive.